Alright, so in this video we're going to be trying to find out the angle of attack for our airfoil in which we have the greatest lift-drag ratio, so we can find out the most efficient angle at which our airfoil will operate. In order to find out the lift-drag ratio, all we have to do is take our lift and then we divide it by the drag. So right here I have my data that I got from my wind tunnel testing, and I can see the different angles that were tested and then the lift and the drag that were associated with each angle. And at this point I kind of am going to have to do a little bit of trial and error in order to find out the greatest lift-drag ratio. So I'm looking for the largest number. So I'm going to start at, let's say, angle 8. So the lift-drag ratio is lift divided by drag, so I'm going to go ahead and do 0.4 divided by 0.1. And I can use my calculator to do that if I need it. And I find out that my lift-drag ratio was 4. Alright, so now I'm going to go ahead and I'm going to keep going. I'm going to see if I can find a lift-drag ratio that has a greater value than 4, because I'm looking for the largest one. So I'm going to go to 9, and that's 0.6 divided by 0.3. 0.6 divided by 0.3, that's actually going to be 2, so that's a little bit less. Go to angle 10, 0.8 divided by 0.1, 0.8 divided by 0.1, and that's going to give me a lift-drag ratio of 8. Alright, so that's my greatest so far, and I'm going to keep going. 11, we've got 1 divided by 0.1, or 1/10. And that's going to give me a lift-drag ratio of 10. Okay, so once again I found a larger one, so that was angle 11. Angle 12 is going to be 1 for lift and 3/10 for drag, so 1 divided by 3/10. And I end up with a repeating decimal, so I'm going to round this to the hundredths place. So 3 and 33/100ths. Okay, and I'm going to keep going. Angle 13, we have 1 and 1/10 for lift and 3/10 for drag. Alright, that gives me a little bit larger one. I'm going to round to the hundredths place once again. Alright, and then for angle 14, I've got 1 and 1/10 divided by 4/10. Okay, and I can see that my lift-drag ratio is actually starting to get a little bit smaller. I'm going to go ahead and let's try another one. Angle 15, we've got 1.3 divided by 3/10. Went back up a little bit, so 4 and 33/100ths. So I'm going to keep going, and we got angle 16 is 1 and 5/10 divided by 7/10. Okay, and it's gone down. And I'm going to keep continuing until I start to see a pattern where my lift-drag ratio starts to get lower and lower. If I notice the pattern is that it's getting lower and lower and it's not starting to increase again, at that point I can stop and look and see which lift-drag ratio was the largest. In this case, when I got the lift-drag ratio of 10, that was my largest value. And that means that the most efficient angle of attack for my airfoil was when the angle was at 11 degrees. So I'm going to go ahead and record that data down. So my angle of attack was at 11 degrees. At that point, at 11 degrees, the lift was 1 and the drag was 1/10. So my lift-drag ratio ended up being 10. Okay. Now the second part of this is you want to find out at what angle does your airplane stall with the airfoil that you have, the wing that you attached, and then also how do you know that that's where the airplane stalls at. So to figure that out, I'm going to go ahead and look at my data once again, and this time I'm only interested in the lift. And what I'm going to do is I'm going to scan my lift, and I'm looking for the point where the lift values stop increasing and they start going back down. At that point, that's actually the stall point when you start to lose lift as the angle gets greater. So we can see between the angle of attack of 30 degrees and 31 degrees is when my lift values begin to decrease. So my stall point is actually going to be 30 degrees. So when my airfoil, my airplane wing is tilted at an angle greater than 30 degrees, I begin to lose lift, and that would be my stall point.